Hello and welcome to everyone to the 33rd lecture on the financial econometrics. In continuation of the last classes, we will discuss about the multivariate time series modeling. So in that, today we will be discussing two important concepts of the multivariate time series analysis, that is cointegration and the vector error correction model. From the previous classes, we know that if we have the two non-stationary series and we regress one on another, in that case, what we will get the result will be an spurious regression. That means the results will be misleading because in that case, the t statistics becomes significant, though there will not be underlying actual relationship. Then what is the solution we got? We got the solution that we have to difference those series and make it stationary. Then we use those stationary series for further analysis. However, during this process, we will be losing one observation. Though it seems one observation, but if you remember, we will get a series of delta yt is equal to yt minus 1. Then we will get delta yt minus 1 as the yt minus 1 and yt minus 2. So basically, we are losing the series of information. So basically, the moment we make the stationary series by differencing, we lose the information. Then what is the solution of that? The solution of is the cointegration analysis. So in case of cointegration analysis, it is useful to retain the meaningful long-run relationship. However, we cannot always use the cointegration analysis in every case of non-stationary series. So let's understand what is the cointegration. So cointegration is basically a statistical property where if the two non-stationary series are combined linearly, the resultant series is basically becomes stationary. So that property is known as the cointegration. And this implies that there is the long-run relationship between those non-stationary series despite the short-run fluctuations. And this phenomena is quite useful, especially in economics and finance, where we have a lot of individual series which are trending together. That means they are non-stationary. However, there is the relationship. For example, let's take the income and consumption. We know that as income increases, the consumption also increases. So both are following the similar trend. So this trending non-stationary series, if we wanted to find out the relationship between this income and consumption, then we have to make it stationary by differentiating. However, once we make the difference, we will be losing very important information. So in that case, this cointegration comes into picture and it helps us to find out the relationship of such variable which are non-stationary by nature. So the mathematical interpretation of the cointegration can be represented is, let's assume here we have the two non-stationary series yt and xt, that is both are integrated of order 1. Then if we can represent the linear combination of yt and xt, let us say by a variable zt, where zt is the yt minus beta xt, and if the zt becomes stationary, so yt and xt are the non-stationary and the linear combination of these two is the zt which is stationary, then we'll call that this xt and yt are cointegrated, and 1 and minus b is beta is known as the cointegrating vector, which basically represents the long-term relationship between xt and yt. Let's generalize that into the more than two variables. Let's say we have the different variables and those are integrated of different orders. Then if we combine those variables, let us say here, if we have the k variable and we are combining those variables with the linear combination of this form, that is here zt is basically alpha 1 xt x1t plus alpha 2 x2t so on up to let us say k, that is alpha k xkt. Then the integration order of zt theoretically will be the maximum order of any of these variable. So let us say x1 is integrated of order 1, x2 is integrated of order 2, and x3 is integrated of order 3, and that is the maximum order of integration. Then the order of integration of zt will be equal to the order of integration of x3. So that's what we mean by, and that is the general rule we have. If we combine any non-stationary series, then the combination of those non-stationary series will be itself the non-stationary. So we can represent here zt is equal to alpha xit, and with little mathematical manipulation we can write this equation as xit. So basically what we have done here, we have done this x1t we have taken here this side, and here we have now this we have taken alpha 1 x1t, and here we have alpha 2 x2t plus alpha 3 xt3 t plus up to alpha k and xkt, minus we have this now zt here. Or if we take this alpha 1 this side, then we can write x1t is equal to alpha 2 upon alpha 1 x2 t plus alpha 3 upon alpha 1 x3t. Similarly, we can write alpha k upon alpha 1 xkt plus zt upon. So the mathematical manipulation what we have done here, we can this particular equation we can write here, this x1t is equal to alpha 2x2t plus, similarly we can go up to alpha k xkt. So all those except alpha 1 is this side we have taken, all other is there, and then this zt we have taken this side minus zt. Now if we take this alpha this side, then we can write x1t is alpha 2 upon alpha 1 x2t plus alpha k upon alpha 1 xkt minus zt upon alpha 1. And this basically here we have this particular equation. Now here we have taken alpha 2 upon alpha 1 is nothing beta 1, alpha k upon alpha 1 is nothing but beta k. So it starts now from I1 to k. So this we can represent here, where the beta I is equal to minus alpha I upon alpha 1, and this zt prime is nothing minus zt upon alpha 1. So after this manipulation, if we see here, this is nothing but an example of linear regression equation, where this xit x1t is equal to these variables, and this is nothing but will work as an error term. So this zt represents an error term, and this particular equation represents an OLS regression here. So what is the property of this error term? So this error term has two properties. One, it is non-stationary, because we know that the combination of non-stationary series is non-stationary. Another thing, it will be autocorrelation, because it is depending on the, it is non-stationary, so it is depending on the previous observation. So this zt prime, which works like an error term in the previous equation, it has two properties. One, it is a non-stationary. Second, it is the autocorrelation. However, let us say this zt, which is k by 1 vectors variables, then the components of zt are cointegrated of order d and b if all components of zt are id. We know that is integrated of order d. However, if there exists at least one vector of coefficient alpha, such that this alpha prime zt follows the order of integration d minus b. Then we will call that this all those variables is cointegrated of order d and b. So what it means basically, let us say if the highest order of integration is 2 and the resultant zt is integrator of order 1. So that means there will be the one cointegrating vector. If let us say the highest integration order of a variable is 5, then zt is supposed to be the integrator of order 5. However, there exists at least one value of alpha which makes this zt as or integrator of order 2. Then there is the difference of 3. Then we will call the x variables are cointegrated of order 5 comma 2. So that's what we mean by the cointegration. Now what is the economic interpretation we have cointegration? This cointegration is very crucial for detecting the stable and long-term relationship between the economic variables which is fluctuating within the short run. But what is the long term, what we call the stable relationship? Then we have to go to the cointegration. For example, let us say this consumption income, which already we have discussed, that if both are trending, but if they are cointegrated, their long term relationship will be stable. And we know from economic theory, these two in the short term may change and they follow the similar time trend, and we cannot, and will be non-stationary in nature, so we cannot find the relationship between consumption and income, though the theory says both are the related. So in such situation we may use the cointegration. And another example we can take from the financial markets. For example, prices of assets in the same sector may be cointegrated, reflecting the share underlying factors. However, at the level they will be non-stationary, so we cannot find the relationship using the regression. Or if we are going to difference, then we will be losing the information. So in such cases, we turn to the technique of cointegration. So let us take another example here, then money demand function. So we know that the money demand function depends on here this MT, the money demand, and it depends on the price level, it depends on the real income or the output, and it depends on interest rate. However, what we know, all these factors, price, income, and the interest rate, all are basically in the short run non-stationary by nature. It will be fluctuating in the short run. Though this kind of, there is the relationship between these. So what is the solution? So one solution is to take the differences of this series. However, in such cases we will lose the information. Then another is, if they are cointegrated, then we can find out the long-term relationship using the cointegration. So that's what we have discussed here. What are the implications we have? That a cointegrated relation suggests that despite the short-term fluctuations or deviations, there is a force which makes basically pulling all those deviations and bringing them to us to the long-term relationship. So we can assume a flowing river. So both the side of the river may fluctuate in the short term, but in the long term, if we see a long view, we can assume the width of the river is same. So that's what we mean by the cointegration. A short term, the series is may move to this side or that, but in the long term, they are coming to us to the average relationship. Then there is a related concept of this error correction. So basically what we have, the short term deviations. So there will be a force which will correct them. They will be pulling to us to the equilibrium. This error correction term basically takes us to the next model, what we call the error correction model. It is also known as the equilibrium correction model. So this model helps us to model this kind of long-term equilibrium relationship where there will be adjustment in the short term. So when these two variables are cointegrated, short-term disequilibrium lead to adjustment back to the equilibrium. That's what we call the Granger representation theorem. And based on that theorem, we have the error correction model. So This ECM allows for the simultaneous modeling of the both short-term relationship as well as the long-term relationship. So how we incorporate the both short-term and the long-term relationship in the error correction model. To understand that, let us say, before that we will see how it removes the problem of the spurious regression which we found in case of non-stationary series. So this long run relationship on the short so this ECM allows us to estimate both short term and long term relationships simultaneously. We do not have. If you remember in the previously what if you remember previously what we used to do to solve the problem of the spurious regression, we used to take the difference. However, when you are taking the difference, we are not able to estimate the long term relationship. We used to establish only short term relationship. However, this ECM, the error correction model, helps us to establish both these. And this ECM has been derived from the Granger representation theorem. So what is this theorem says that? This theorem says that if yt and xt both are cointegrated, then their relationship can be represented by the model error correction model. So how we do that? To understand, let us take the two variable cases here. So we can decrease delta yt on phi plus alpha y, yt minus beta xt, and then the difference, and here also the difference variables, and this is the epsilon of this. So if you remember basically what we are doing here, this part is nothing but representing the co-integration relationship. So if we have a vector of 1 and beta such that this non-stationary series yt and xt, combination of this becomes stationary, which we may represent using this ut hat minus 1. If we are using ut minus hat gamma here, then in that case this adjustment coefficient alpha y or this gamma basically represents the speed of adjustment or the speed through which it is returning to us to the equilibrium relationship. So that's why this term yt minus beta xt minus 1 is known as the error correction term, and from here the name has been derived error correction model. And here we have both short run as well as the long run component. The short run components are represented by the difference variables, coefficient of the difference variables, and long term has been represented by this error correction term. Now, how we have removed the spurious regression? Because here these components are regressed on the difference variables, that is delta yt and delta xt, which is obviously is now stationary, and it has been regressed ut hat minus 1. So which is the linear combination of the two integrating vectors. So once we have this structure of the equation, then we can use the simple ordinary least square to estimate the variables. However, what is the drawback we have, or the downside of this structure we have, that it is assume of the single equation model here we assume. Then how to detect there is the co-integration? Because once they are co-integrated, then only we will be able to use the ECM model. So there is the Engle-Granger test we do. So what is the Engle-Granger test? The test is basically for no co-integration. So null hypothesis is that there is no co-integration. So there are the two steps we have, what we call the two-step Engle-Granger test. In the first step, we make the order of the variables. We have the two variables xt and yt. Then which one is dependent, which one is independent, we have to make. So let us say we are assuming yt is called alpha 1, alpha 2 xt and nu t. So here we are assuming yt works as the dependent and xt is the independent. This is the order of the variable. Or we can have xt as the dependent and yt as the independent. So let's assume the first equation we are assuming as the order of the variables. Then the next step is that we'll estimate that particular equation, then evaluate the property of the estimated residuals. So what property will evaluate? Whether the estimated residuals are stationary or not. So that's the basically how now we will do that. So to to examine that property, we will use this regression equation. So this is the nu t is the estimated residual. Now that is regressing on the like term of this, then now we have to evaluate the value of phi 1. If the value of phi 1 is equal to 1, that means this v nu t estimated residual is non-stationary. So in that case, there is no configuration because xt and yt was assumed to be integrated of order 1. So there is no change in the order of integration. However, if this phi is 1 is less than 1, that means this series is stationary. Then we will say there is the configuration. So since this yt and xt both were integrated of order 1, now the linear combination of these two results in this estimated residuals becomes stationary. Why it will be stationary? Because the phi 1 is less than 1. Then in that case we will call there is the configuration between xt and yt. How to test? Obviously we can use the t statistics to test the whether this phi 1 is less than 0 or is it equal to less than 1 or is it equal to 1. However, in this structure we have certain issues, certain problem we have in case of Engle-Granger process. What problem we have? First, we have to ascertain the order of the variable, whether it is yt as working as the dependent or whether it's xt which is working as the dependent. So there is the problem of ordering of the variables. Then it could be possibility if we are using the first order, then we may find the estimated residuals follow the integrator of order 0, that is stationary. So that means there is the cointegration between n and xt. However, in other case, it might be possible that this omega t, that is thus if we change the ordering of the variable, now it becomes there is no cointegration. So then how to decide whether these two series are cointegrated or not? So then we have this issue. Another thing, this fails to give the number of cointegrating combinations. It gives only one value of alpha such that these are the cointegrated. However, there is possibility it may have more than one combination. So it does not tell us how many such combinations do exist here. And especially that becomes when we have the three variables. So don't know which variable adjusting, which variable is pulling the other variable, and which variable is fluctuating in the short run, and which one is pulling that into the to the long run equilibrium. We will not be able to find out that. Then what is the solution? That in such cases the solution is basically vector autoregression and the vector error correction model. Then here the basically two-step procedure we have in the VECM or the vector error correction model. So error in the first step will carry over the second step. That is, error in the vector autoregression will carry over onto the. So we don't know which variable you are adjusting. Another problem we have, it is a two-step procedure. So first we have to find out, estimate the linear regression. Then in the second we have to find out what is happening with the error term. However, if let us say if we are making mistake in the first step, that error, that mistake will be carried over to the second step. So these are the problems we have with the Engel and Granger process. Then the solution is basically vector autoregression and the vector error correction model. So what is the vector error correction model? So this is basically nothing generalization of the error correction model. Error correction model was limited with the two variable case. Despite with their all limitations, we generalize that into more than two variable cases. And this solves the problem of error correction model. So VECM is basically nothing but it is the reparameterized version of the vector auto regression. In case of where what we have assumed vector autoregression is stationary model. So when the root of this characteristic is less than 1, we assume the estimated vector autoregression is stationary. If not, then what we do? Make the series stationary, then use the vector autoregression. Then in that case, Again we have the problem. What problem I have? The long run information is lost. Then what is the solution? If we have, the solution is vector error correction model. So what is the vector error correction model? It's basically nothing but the reparameterization of where. How we do that? So let us consider we have a vector autoregression represented by this particular equation. Then we reparameterize this. How we reparameterize this? We use this delta yt alpha zt minus 1 tau 1 delta yt minus 1 tau 2 delta y up to order p, and here we have epsilon t. So where this zt is beta prime yt minus 1. So therefore this alpha zt1 is alpha beta prime yt minus 1, and this is nothing but equal to pi yt minus 1. So we can represent this structure into the form of this, where this is the pi yt minus 1, this all other series we have this practice. Now remember, this pi we are representing for one leg here. So there could be more than one leg in the Z2. So in that case, this pi we can generalize. So we can say this pi is nothing but pi 1 plus pi 2 plus pi 3 up to pi p minus this identity matrix, and we can represent this tau p minus 1 is nothing but minus pi p. So that is the basically represented. In concise way, the whole system we can represent the VECM in like this, where delta yt is equal to alpha b prime yt minus 1 plus the summation tau I delta yt minus I from 1 to p, that is the lag order we decide. So we have the multivariate case, we can represent this vector error correction model. Then here this is the matrix pi is nothing alpha b prime captures the cointegrating relationship as we have seen in the bivariate case, and this alpha is speed of adjustment towards to the equilibrium. This difference value, the coefficient of this difference value represents the shorter relationship, and this beta is the cointegrating vector representing the longer term relationship. So in this case of VECM, we are able to represent both short term as well as long term relationship of such variable which are non-stationary and cointegrated. Then the problem comes, how we will detect the cointegration, or what will be the cointegration in this particular structure. Then in that particular structure, this rank of pi matrix which we represent using the raw gives whether the cointegration exists or not. So if raw pi is equal to 0, that is the rank of that pi matrix is equal to 0, that means there is no cointegration. If raw pi, that is the rank of this pi matrix, is 1, then there will be one cointegrating vector. If it is 2, then there will be two cointegrating vector. So maximum it could be less than or equal to k minus 1, there will be more than one cointegration vector. So it will basically depends on the rank of this matrix. So how we detect that? So for that we use the Johansson test for cointegration. So this Johansson's test basically helps us to determine the number of cointegrating vectors into the multivariate system. So based on this rank of the pi matrix in the VECM represent the number of cointegrating relationship as we have discussed here. It is very useful in case of multivariate system to find out the cointegration and to find out the stable relationship. So this is the structure we will be using for this cointegration. So delta yt is here pi yt minus 1 tau. So this is the same structure. Here we have added this particular term to basically represents the intercept, trend or seasonality. So all those is we may capture using the matrix dt here. Then this test of cointegration between y's, this all the y values is calculated by looking at the rank of this pi matrix. We use the two test statistics are there. One, what we call the lambda test statistics, where this lambda test is basically nothing. This lambda I are the ordered Eisenhower value, and this t is the nothing but the sample size. Another we had maximum Eisenhower value. So this is the trace statistics, and the second one is the maximum eigenvalue. However, in both cases, so we have the two statistics, that is lambda test statistics and the maximum eigenvalue. This how we interpret the result. This lambda test statistics tests the null hypothesis that the number of cointegrating vector is less than or equal to the R against an unspecified alternatives. So lambda test is equal to 0 when all the eigenvalue is equal to 0. So it is basically a joint hypothesis test. Lambda max, that is the maximum eigenvalue test, tests the same null, that the number of quantity vectors is R against the alternative of R plus 1. In both tests, the decision rule is this: the null hypothesis is rejected if the test statistics exceeds the critical value, suggesting that the existence of additional cointegrating relationship. So basically here we assume in the first case there is no cointegration, that is R0, that will be the null, against the alternative of R is more than 0. Then here we get the second step, that contiguous vector is 1 against alternative this is more than 2. So if we reject this, that means there is at least one contiguous vector. If we reject this, that means there is more than one contiguous vector. So we can summarize this in case of VECM, how we do that, what is the estimation process we have. The first step, we test for the stationarity. We can use either any unit root test, for example, augmented decay Fuller test. So we check whether all the series are I1, that is non-stationary or not. Then the second step is test for the cointegration. So we can apply the Johansen cointegration test in case of multivariate, that is more than 2 variable, or in case of 2 variable we can use the Engle-Granger method. So this gives us the number of cointegrating relationship. Then we construct that the VECM. Then we can use the estimate the VECM model, either the maximum likelihood estimation model, and then we estimate those parameters. That means there are the two situations. One, the series should be non-stationary. Let us say I1. Both the series xt and yt. Second condition is that both xt and yt should be co-integrated. Then only we will be able to use the vector error correction model. And this is the procedure we should follow. So ultimately what we can conclude, this cointegration VECM are the powerful tools to estimate both short-term dynamics as well as the long-term relationship. This model helps us in understanding the stable relationship many economic and financial variables. And these models help us in understanding the stable relationship between this economic and the financial data, even with the non-stationary time series. There is the many applications we have in the macroeconomics, micro, as well as in the financial data. So today we have discussed about the concept of cointegration, and if there is a cointegration, then how we can switch to the vector error correction model, and how these models are superior than the differencing. Then see you in the next class. In the next class, we'll be discussing about how we can make the interpretation of such models. Thank you so much.